Okay, so welcome to the online class this time. This is September 26th. This class normally is conducted in person. However, this time only, it's carried online by the student's request. There we go. Yeah, we talked about the test. So, telecommunications, TELE 1022, TELE 1022, telecommunications course, Fanshawe College, London, Ontario. All right. Here's the verbal header. Okay, so I will be jumping between certain presentations today because there are some slides that I have done for other subjects that actually give you some better detail with this one here. So, but this is the main presentation that we're going to carry on, and I will upload this one today along with the other ones, but I'm going to just point you to the certain slides only from that one. However, you will have the whole presentation uploaded. Okay, so transmission line theory. So remember when we have the model of whatever the transmission equipment and the receiving equipment, and over here we have the link. And what do we have? What do we distinguish as links? Remember the three things. We have the copper, we got the fiber, and we have the air. Today, we're going to concentrate mainly on this copper part of the link. And copper is the metal conductors. Sometimes it could be aluminum, sometimes it could be gold or silver. However, as the metal conductors, to make things, to simplify things, we just call it copper. What did I do? What did I do? My mouse has jumped the trigger. Okay. So transmission line theory, transmissions, line functions and characteristics. We have gone through some of the characteristics of some of the lines, and this is going to be kind of more put together towards that way. So, okay, in this section, we will take a look at the various types of transmission lines. We won't go over the whole thing over this 1 hour, so we'll continue that next time, whenever that will be, probably next week. So types of transmission lines that connect telecommunication system, which I just showed on the picture. We will define these lines as conductive connections that carry the signal power, in other words, the links. In many cases, the same types of lines can also carry power. In some applications, they can carry both electrical power and signal power. What would be the example? Okay, let me see the example here. All right, so let's say we have a switch. Right? In the equipment, so this is a LAN example. LAN stands for local area network. And we have the LAN room here, communications room with the equipment rack, standard 19-inch from end to end here. And over here we have maybe something that's called a patch panel with all the ports. And over here we have something that's called a switch with all the ports and whatever other equipment we're going to have here. So the main link between the switch and, for example, the destination location. So here's the data port, Ethernet port. We have dry connections between the patch panel and the destination. So this is just a dry connection, straight link on one-to-one basis. Each pin is connected to the same pin, and of course it has to be connected a certain way. Now from here, each port is patched from the patch panel. Patch panel. All right, and here's the switch. It's P patch panel. Here's a switch. Okay, so on a one-to-one basis, so whatever those destinations are going to be, desktop, wall-mounted, ceiling-mounted, whatever the smart devices are connected, those are dry connections. And then on one-to-one basis, they're connected to a switch. And switch, in short, can be considered as, well, the traffic controller for all the Ethernet signals. Now, let's say we have a PC on the other side here. All right, here's the keyboard, here's the monitor. All right, that's the PC. All right, PC. Excuse my drawing skills. So from the PC, there's going to be a patch cable connected to here. Now, the Ethernet cable is going to transmit and receive both at the same time the data that travels between the PC and the switch. The PC is plugged in to the wall. Okay, power. So whatever the signal is there on the output port or the Ethernet card port, the signal is already going to get the power from the PC. And the switch also gets its power. It gets its power from the wall. So this thing is plugged in, that thing is plugged in. All we need is the signal transfer. However, let's say we have a VoIP telephone system. All right, a VoIP telephone. Or on the other side here, we might have something like wireless access point in the ceiling. That's the Wi-Fi connection. And this is in the ceiling, and that is connected here. Now, the VoIP telephone is an active device, voice over IP, VoIP telephone, that is basically just like a PC, but it doesn't have this has a different type of monitor and it has a handset. So, but the data basically is in the form of Ethernet that travels between the phone and the switch. The phone has to be powered. So what you can do is you can have a power adapter like that, and that is going to be plugged into the wall, and that is going to be plugged into the phone to power the phone, and so the signal gets its power, and between that and the switch, so the signal has a possibility to travel. Wireless access point, the same thing. You can have a power adapter plugged into the ceiling, and it's going to get its power from that, and the signal is going to have the possibility of having some sort of energy to travel between the wireless access point and the switch. So in this case, the data cable, which is our link, which is our copper link, transmits only signal. Over here, there's no problem because the PC is plugged into the wall. Usually there's going to be a hydro outlet by the PC, so no problems here. Over here, this telephone can sit on a desktop, and desktop can have a power in its proximity, so no problem, sort of no problem there, except for the additional wires that sometimes you might not want to have. Over here, there could be no problem, or there could be certain type of challenge to deal with because this wireless access point is in the ceiling. So in order for that to make that work, you're going to have to get the electrical company, whoever that is, to install an outlet in the ceiling so that power transformer can be connected. The power supply can be connected to the wireless access point so the signal can travel. That is not a very practical solution. So what they developed, and I call it the quote unquote they, all right. What has been developed is something that's called a PoE, power over Ethernet. Okay. So there are different types of switches on the market. Different brands produce different type of switches, D-Link switches, Cisco switches, whatever else switches. And usually the switch has the capability of transferring signal. Well, if you want to escape the inconvenience of having the electrical outlet being installed somewhere in the ceiling, you can use PoE. The switch can have the capability of power over Ethernet on each port. Now, whenever you're ordering a switch, you need to know whether you need a switch with PoE or not, because not all the switches have the PoE capability. So you have to make sure that the switch that you're ordering has PoE capability. And some of the switches, some of the more expensive switches, will have power over Ethernet on all the ports. And some of the switches going to be specified that maybe the first 8 ports are going to have PoE and the other ones are just a signal. What does that do is that on some of the pairs, because the Ethernet cable has 4 pairs, on some of the pairs, there is going to be power, DC power, usually 48 volts DC, but there are some other devices and other systems that use different type of voltage. So you need to make sure that this device is specified for a certain type of voltage, and the switch is able to provide that voltage. Plus, also you need to know the specifications of the switch to see if in total it has the capability of powering up all the devices. So there are different ratings for the power availability on the switches. So in this case, the power is transmitted along the signal. It's superimposed on some of the pairs, and it's plugged in into the wireless access point, for example, or it could be a security camera. Then this device is going to have some discriminatory circuitry that is going to discriminate the power and is going to send it to the power circuitry to power the device up, and some of the signal is going to go where the signal is supposed to be. So it's going to have some circuitry to differentiate between power and signal. It's done internally. So in this case, you do not need to have the power adapter. And so in this case, the signal, the cable, the link transmits signal and power. This is just one of the examples. All right. So right here, in many cases, the same type of line can also carry power. And in some application, power, and in some, okay, see, that's why I need to, as we go along, there, before I forget. In many cases, the same type of lines can also carry power in some applications. Okay. They can carry both electrical power and the signal power, or the signal, period. Right? Will be the examples B, and I just gave you that example. In all types of transmission lines, we will have losses, and understanding those losses is critical to a robust system design. Okay. Again, let's say we have something that's called CCTV system. they were much more popular some years ago, but you can still have those. CCTV, closed circuit television system, and it could be, let's say, television sets with the coaxial cable on with the channels for the TVs being distributed over a large building such as school or hospital. Or it could be the security cameras. But let's say we're dealing with the television sets distribution. So we're going to have something that's called an RF amplifier. Let me just draw it like this. Here, symbol for an amplifier. Right? So here's an RF amplifier, radio frequency amplifier. And from there, you're going to have some kind of a signal of whatever the dBMs power. Okay. Now, from there, you're going to have one main bus line, and you're going to have television set in every classroom, for example. Let's say this is 200 feet. 200 feet from here to here. End-to-end cable, as an example. So from here to here, it'll be 200 feet. Now, a coaxial cable will have certain amount of loss per foot of the signal. So now, and then, of course, the television set is going to have certain amount of dB requirement. It cannot be too high. It cannot be too low. So I'm going to have a certain amount X for all of them. Now that X amounts, it's going to be between certain amount and between certain amount. It has to be relatively low to the whole signal being transmitted. Here's the big signal. So what do we do here is we are going to install things that are called taps. At every location, there's a tap. You're just tapping in to the main line. And each tap is going to drain a certain amount of signal into every TV set. Now, there's going to be a certain amount of gain provided by the amplifier, and the signal is going to be huge, going from here all the way to there. Now, this tap is going to have to be calculated to deliver the specific amount of signal. Just draw a little tiny bit of the signal and deliver it to that TV. But the tap has to be calculated depending on what kind of a strength of the signal is here, based on the signal strength on the output of the amplifier right here, and to the point that it gets here. This cable is going to have certain amount of signal loss based on its distance. And then by the calculated strength of the signal, by calculating the output and whatever is calculated to be here, then a certain amount of tap, certain size of tap or certain specification of the tap has to be applied. Then that signal is going to be that much less here, plus over here, plus the signal loss over the distance here, and then another tap has to be calculated, and so on and so on. It's a treacherous calculation. This type of calculation, you just start from here, calculate the taps, work your way backwards to see if everything adds up, and sometimes it doesn't, and you go back and forth, making sure that those taps that you're going to order once, because sometimes it takes a week or two for those taps to arrive. and you don't want to make a mistake, because if you make a mess, if you mess up somewhere here, you're going to affect the whole all the other signal down the road or down the cable here, right? So all types of transmission lines will have signal losses, and understanding those losses is critical to a robust system design. Right? Now, although we will be looking at the conductive connections, with copper being the most common material used, other materials like aluminum also can be used in many applications, but for the most part, we just call it a copper to simplify things. Although we are seeing wireless transmission finding its way into many applications, there are still many applications for transmission lines. What are some of the examples of a transmission line is more suitable than wireless? Well, if you go to Toronto, to the financial district area, like the, well, Church and Bloor, okay, Church Street and Blue Street West or Blue Street, that's you're going to see a lot of those business high rises there. Each high rise will have maybe 50, 60 floors, and each floor will see, they don't seem like much from outside or from the distance. But once you enter that building, you just get to feel the size of this whole building, and one floor is capable of hosting maybe two, three, four, sometimes five different businesses. Every business will have a certain amount of computers. So there could be something like 300, 400 computers on every floor. Do you think we're going to have enough wireless bandwidth to accommodate that for the next floor and the next floor and the next floors to avoid the interference and all that mess? Not likely. Okay, so there's nothing like a good wired connection. Other things, for example, there could be some highly secured businesses. Like, for example, we used to, well, when I was in business, I used to install different LAN systems, and whenever we had, especially the banking institutions, usually the banking institutions wanted to have nothing to do with the wireless. You're not talking about the bank that you go to cash your check or do whatever business that you walk in. You're talking about the bank office that is not open to public, and they just have their office people doing the office things that they do. Right? And those people, they don't want to have anything to do with the wireless systems for the purpose of the security or security of the whole data network. Uh, so in those cases, we would not do any kind of a wireless installation. And even in those banks that you walk in, there is a network that is separated. The network that has to do with the administration of the banking is a separate network that has to do with the Wi-Fi connection or the wireless. Of course, these days everybody wants to have a Wi-Fi password because they want to see the score of the baseball game or whatever. So those two networks are going to have quite often two different internet providers. They will have nothing to do with each other except maybe being in the same room, or sometimes even in different rooms for the purpose of security. And they'll have different modems, different complete wiring sections. So for the consumer Wi-Fi thing, it's going to be completely different internet. Sometimes in different internet provider. And whatever has to do with the banking from the professional side or the corporate side, that will be all wired. No any wireless things for the purpose of the security of the so the data is secure. Um, so yeah, so when sometimes people say that wires are going to be pried out by the wireless systems, in my professional opinion, is that they don't know what they're talking about. Of course, I could be wrong, but not likely in this one. Is it possible to replace all wired system with? Okay, we just answered that question. All right, transmission line types. There are many types of cables. Often selection is based on the application, price, performance, environment, and availability. Frequency of the application is often most critical parameter. Okay, the frequency of the application is often most critical parameter, and generally, high frequencies relate to higher cost of the cable solutions. In some cases, the interference, or sorry, the interface requirements and applications will determine the type of cable that might have to be used. So, and there might not be any alternatives. That has to do with the time division multiplexing and the frequency division multiplexing. Like, for example, here's a coaxial cable. It has a huge bandwidth. As opposed to a data cable that it doesn't have as much bandwidth as a coaxial cable, and the bandwidth is has to do with the analog radio frequency signal that we can take it up to a certain amount of frequency. How high can we have frequency transmitted from one end to the other, and the signal is going to be not distorted enough, so the signal can be understood on the other end of the cable. So usually with the coaxial cables, we're going to use that with the frequency division multiplexing, and it's a very sophisticated terminology. It's a mouthful. So frequency division multiplexing, which is basically we have channels, channel 1, channel 2, channel 3, and as we move up with the channels, we increase the frequency until we run out of the frequency that the cable can carry. Then there's the twisted pair. It's said that's a twisted pair and it's drawn as not twisted pair, but it's a twisted pair, which is basically the Ethernet and the phone cable, but most likely it's an Ethernet cable. Then there's that another antenna cable, which is twin wire. Then some narrow conductor interface and the telegraph lines that you can see still hanging or dangling from the old telegraph poles. If you want to get sentimental, get your black and white camera and take some pictures and put some music to it, and you will have some sentimentality going on with the telegraph lines, because I don't think anybody is using telegraph in the world and in this world on this planet anymore. Although I could be wrong. Okay, why are we not switching slides? A two-wire ribbon cable. One of the most basic cables is a twin lead with two conductors embedded in a low loss dielectric. So there's two wires straight, and they're separated by an insulator, dielectric. There's also an open line version as well with exposed conductors. Neither was very popular, although they are low cost. I remember being from Europe sometime in when I was a kid during 70s, and even some of the early 80s, you could see some of those twin wire, twin lead antenna cabling going from, like, usually in the apartment buildings, from everybody's window going up to the roof, and there would be antenna on the roof. The world looked different then. Okay? So all those apartment buildings would have tons of antennas just so people could receive their television signal. And this was a very popular antenna cable. Applications include television antennas, leads. However, most systems today use coaxial cable instead of that. Coaxial cable provides much improved shielding to reduce noise pickup. Multicolor and multi-conductor ribbon cables are still quite popular for low-frequency digital applications. Excuse me. The only thing that I can see that multicolor or ribbon cables or multicolor cables would be still used in some of the telephony applications. So we do have something that's called a twisted pair, 25 pair cable, and the 25 pairs are color coded, so you know which one is pair one, which one is pair 17, and so on. Up to 25 pairs. There's also 100 pair cables, which are 25 cables embedded or enclosed, should I say, in one jacketing. Okay? Um, or just simple data cables for lower frequency. Why do we have lower frequency? Because data cable, when on this inside side of the modem, which is the inside of the building, we have a digital signal going in using the Ethernet protocols. Right? And that's a digital signal, and quite often this thing, well, it is using something's called time division multiplexing. So sometimes one channel at a time is being provided to the, well, Ethernet protocol is, we're just carrying one channel anyways. Okay, so because it's things are connected on one-to-one basis. But there would be something that's different type of communications, like for example, providing the telephone lines in the term of something that's called T1, T as in Thomas, Tango, one in North America, and E as in Echo, E1 in India and Europe. Okay, I'm not sure what Asia uses. And that would be two pairs of twisted pair, which is basically looks like two pairs of telephone line, and one is serving as transmission, the other one is saying as receivage. Okay, and signal can be modulated onto those lines. So on that two pair connection, you can have maybe 24, 25 telephone conversations going on. And that would be in a frequency division multiplexing. Now, some of the applications that utilize connecting certain modules, maybe alarm systems that use one pair of cable to transmit data between multiple keypads and multiple smart devices, they could use something that's called a time division multiplexing, which means time division multiplexing. It would be something like you have different channels. Channel one, channel two, channel three, channel four, channel five, let's say five channels on one side, and you have five channels on to one, two, three, four, five. And you have a telephone connected here, telephone connected here, telephone connected here, and so on. You got five telephones. And over here, you have five telephones as well. All right. And let's say you only have one pair of cables connecting these two systems. If you only have one conversation, then the connection can be made between this one and that one here. So you have channel one. No problem. But what if you want to have two people talking at the same time? What if you want to have two conversations at the same time? Well, you could have a switching system going on, time division, time division multiplexing, which means that you're going to switch one channel at a time and you're going to transmit that. So let's say you have channel one connected to channel one here for 1 second. And then after 1 second, it switches, only channel 2 is connected through that pair, and so on and so on. You will have few seconds between you can talk. That will be quite annoying. However, if you do the switching extremely fast, and if those connections are synchronized with each other, then you could have 5 conversations. And because the switching happens so fast, the human ear is not going to pick up the switching, and you're going to have the illusion that you have a dedicated hardwired connection for each channel. So that's time division multiplexing, as opposed to frequency division multiplexing, when things are going to be divided by channels, and you need to have all the channels present in the cable. And you're going to have a tuner here and a tuner here, or a mixer here. You're going to mix all those frequencies. But if you want to have both ways of conversation, then you have to have mixer here and a tuner here, and you have a mixer here and a tuner here, and so on. So that's the difference between time division and frequency division multiplexing. So, but if you have frequency division multiplexing, then you need to have the cable capable of a lot of frequency range, so you can put all the channels at the same time. Now, when it comes to time division multiplexing, you don't need the capability of high frequency on this cable, because you only need to carry one conversation at a time, and you're just switching very fast between the channels. All right, twisted pair, Cat3, Cat8 cables. Twisted pair cables consist of insulated wires. Category number defines the design and performance of the cable. The balanced pair wires help prevent crosstalk and noise rejection. However, this type of cable is not used for high frequencies due to the loss and the insulation. So here's one table. This is category Cat3, Cat5, Cat5e, Cat6, Cat6a. There is Cat6e available also. Although not that much popular. And then there's Cat7. There's one more cable that has just come out on the market some couple of years ago or so. This is 2025 right now that we're talking about. And yeah, I'll mention that. So we have no shielding, or we have a shielding. We could have a shielding or not. So it's a twisted shielded pair or untwisted shielded pair. Sorry, shielded twisted pair and unshielded twisted pair. So, and here are some of the specifications. And I have another better table here. Okay, from another presentation. So here's the Cat5, for example, and this here shows the let's just see here. Over here, we have the gauge of the conductors being used, and of course, the higher number of the gauge, the thinner the cable is, it just goes inversely proportional. The lower gauge is the thicker cable. So Cat5 uses 24 gauge conductors, and it does have a twist. The twist eliminates crosstalk. Now, I'll come back to that crosstalk idea here, because I don't want to split our attention into too many different directions. So it does have a twist. Twist is used to prevent crosstalk, and long story short, crosstalk is a signal bleeding from one pair to another, or signal being picked up from one pair to another. So transfer speed, I can see you have two different speeds here. You have speeds, specifications as far as data transfer. You have a bandwidth and you have a transfer speed. And of course, if you can see here, you can see bandwidth, and bandwidth is the ability to transfer analog signal. So analog signal is on the outside of the modem, because internet, believe it or not, is provided to us from the outside in an analog form, just like the radio stations, except on the channels we don't have music, we have internet signal. So this is the capability of how high can we take the frequency and the cable being able to carry that frequency without destroying the signal or attenuating it or pretty much degrading it to the point that the signal is not understood. So we can take up to 100 megahertz and the transfer speed that's on the inside of the modem, which the signal is in the digital form. So how many bits per second? And when it comes to signal transfer speed, when it's digital form, we're talking about bits per second, not bytes per second, but bits per second. Okay, so this one we're talking about megabits per second. If we're talking about storage, then we're talking about bytes. So this hard drive can carry 1 terabyte. And of course, there is no per second because it's just storage. Right? But when it comes to signal transfer speed, we're talking about bits per second, and that's it. It's written in stone. There's no any other way of describing it. It's bits per second. So this Cat5 can transfer 100 megabits per second, and just as a coincidence, those two numbers match, but they don't necessarily have to match, as we can see on other examples. And Cat5e is kind of obsolete, not used anymore. You can still see some of the old installations being used. Now, Cat5e is still going on, but is being pried out by it's Cat6. Seems to be the lowest category cable that is widely available on the market. If you walk into a distributor, they will have a lot of Cat6 on the shelf. And if you want to order Cat5e, it might have to be a special order anymore because sometimes distributors don't carry that anymore. But the gauge of the conductors is 224. It has a tighter twist. And look here, the transfer speed of the digital bits versus the analog signal frequency. This one has 1 gigabit per second. See, there's a bit of a difference here. That's why, just as a side note, if you want to install something that's called a VoIP telephone system with VoIP telephones, voice over IP, the digital telephones, there is a requirement of Cat5e minimum. It will not run on Cat5, those phones. And the maximum length is 300 feet. Of course, it's actually 328 feet end to end, but we try not to install any longer than 300 feet because you still have to account for the patch cables, right, on both ends. And here's the bandwidth, analog bandwidth. Now, 100 megahertz with CCA and 350 megahertz with BC. What does that mean? CCA and BC. CCA, copper clad aluminum. If you magnify the conductor, that's what it's going to look like. Copper is the best solution for the dollar. So that's why we call it copper. If you want to have some highly conductive spaceship type of connections, then you're going to use silver, right? Or gold. Believe it or not, silver being the best conductor, even better than gold. But opinions may vary. Now, if you magnify that to save the cost of copper, some of them have decided that they're going to try to cheat things a little bit. So we're going to make aluminum conductor and we're just going to coat it with copper so that conductor has copper. The electricity thinks that it has copper cable or conductor. Bad idea. If you buy, by the way, if you're trying to shop for Ethernet cable, for the data cable, and you see CCA, stay away from that. Run. That is your cue to run. Please do not even take that if somebody offers that to you for free. because you're going to have something on in your garage sitting, not it's just going to be space occupier. So those cables are bad. They do not terminate properly, and they don't carry the signal properly. They fall apart when you're trying to punch them. I mean, connecting with the IDC connection, which is involves the punch down system. No, don't use that. All right. So CCA, copper clad aluminum, or BC stands for bare copper. That's what you want, right? And those CCAs are going to have really attractive prices. So if you see way cheaper cable, then go, red flag should go in your head, right? So just make sure that's not CCA. Now, some of the CCA conductors are being used in some of the headphones, which is okay because it's manufactured done by manufacturer and just to save the weight of things and some of the cost, but it's okay to use some of that in headphone applications because well, look, 100 megahertz, you still can carry 100 megahertz, and the human hearing range is 20 kilohertz. So yeah, it's well within, so we can carry that. And if you don't have to muck with that, you don't have to plug, unplug, and connect and disconnect those wires. It's done by the manufacturer. Fine, you can have that. So don't, if you look at the specifications of headphones, professional headphones, and you see CCA, don't be alarmed with that one. That's okay. So the bandwidth is much lower than the bare copper. You see here, 3 times as much lower. Now, Cat6 has a tighter twist. It has 1 gigabit per second also, or 10 gigabit per second, the gigabits per second. I'm almost done here. Now, the 10 gigabits per second, it's only going to work for up to 180 feet. If you want to, if the run end to end is longer than 180 feet, then you are diverting back to Cat 5e specifications, right? So if the client says, "Well, is Cat 6 better?" Let's get Cat 6. I don't care if I have to spend more money. So whoa, how long are your runs? So that and then by the same logic, you can analyze the other specifications for other cables. Cat 7A, Cat 8 is being the last. Now, a couple of years ago, they developed a cable that is called a game changer. Right? And that cable truly is a game changer. And actually, the name of that cable is game changer cable. That will give you a Cat 6 specifications over 1,000 feet. And that truly is in the data industry infrastructure a game changer. So you're not limited by the 300 feet mark. Okay, you know what? I'm going to stop here. And we're going to continue the conversation, if you will, next time we see each other. But that's the slide that we have stopped on, and we will meet next Monday with all the review, and maybe we're going to have some sample questions to solve, just so you can be comfortable with things. I'm also going to prepare a little online quiz for you with some of the simple problems. Maybe tonight, maybe over Saturday, I'm going to come up with a few questions, give it to you online as a quiz, just to give you the taste of things. It's going to be not too many questions. It's going to be a light thing for you to go over, and it's going to help you with getting comfortable with some of the calculations that we're going to perform and some of the circuit analysis that we are going to perform. Okay. All right. So that's it. Hope you enjoy your weekend, and I'll see you when I see you next time. Hold on. I have a question here. The quiz, yes, the quiz will be graded, but it doesn't have much weight. I had to put some weight on that quiz, but it's minimal. Have a great weekend, guys and girls.